Hello, today we are going to talk about buffer solutions. Solutions that are capable of maintaining a stable pH when a strong acid or base is added to them. This is often essential in analytical chemistry, particularly during titration. There are also some biological buffer systems. Before we begin, we need to recap a few concepts that you should be comfortable with. First of all, what is an acid? An acid is a substance that donates a proton. And what is a base? A base is a substance that accepts a proton. We also need to recall Le Chatelier's principle. If a system in a state of equilibrium and the conditions change, the equilibrium shifts in the direction that opposes or minimizes the effect of that change. Alright, let's move on. Let's look at the example of an acidic buffer based on acetic acid. How does a buffer work? Weak acids only partially dissociate in aqueous solution. Here is the reaction equation for the dissociation of acetic acid. If we add a certain amount of H plus ions, say we add hydrochloric acid, a strong acid, the equilibrium in this system will shift to the left towards the binding of H plus ions and the formation of acetic acid. However, at the same time, the concentration of acetate ions would decrease, which would normally lead to an equilibrium shift to the right to produce more acetate ions. In essence, nothing would change. The concentration of H plus ions would remain the same. In the same case, adding hydrochloric acid would change the pH because the acetic acid would remain only as dissociated as it was initially. The additional H plus ions would not be effectively bound. But what if we create an excess of acetate ions? We can do this by adding a sodium acetate solution to the acetic acid. If we then add a strong acid, such as hydrochloric acid, to this mixture, the excess of H plus ions will bind with the available acetate ions to form acetic acid. Since there is an excess of acetate ions, their concentration changes very little, and the equilibrium shifts specifically toward the binding of H plus ions to the left. Consequently, the surplus H plus ions are bound by the acetate ions to form undissociated acetic acid molecules. The concentration of H plus ions remains stable, therefore the pH does not change. Moving forward, what if we add a strong base, like sodium hydroxide, to this mixture? The excess of hydroxide ions will bind the existing H plus ions to form water. The neutralized H plus ions are then replenished by new ones formed through the further dissociation of acetic acid molecules. Because H plus ions are being consumed, the equilibrium shifts to the right. Acetic acid continues to dissociate, producing new H plus ions to their concentration remains virtually unchanged, and the pH stays constant. Now let's look at how to calculate the pH of a buffer solution. First, we write the equilibrium constant for the dissociation of acetic acid. Then we express the equilibrium concentration of H plus ions in terms of this constant. We can assume that the equilibrium concentrations of both acetic acid and the acetate ions are approximately equal to their initial concentrations. We substitute these concentration values into the equation. Next, we take the logarithm of the equation to derive the pH formula. Note that the fraction on the right side of the equation is flipped upside down. The numerator and denominator have swapped places. Why does this happen? Because we know that pH is the negative logarithm of the H plus ion concentration. Since we are changing the sign from minus to plus, the fraction must be inverted accordingly. That is all for now. Thank you for your attention, and I will see you in the next video.